Hi, stat students. Let's record our last section of chapter 10. There is more, but this is where we're going to kind of stop talking about residuals. So section 10.3 is all about residuals. So in section 10.2, we wrote our regression line, our y prime equals a plus bx. So now we're comparing what the predicted value is and what the actual value is. So we're using our sample data and we're using our regression line. So first of all, a residual is y minus y prime. So what actually happened minus what predicted happened. So I'm going to jot that down. Actual minus predicted. And we have to do that for every piece of data, every set of data that we've got. So if we have 10 sets of data, we have 10 actual values. And then we're going to take and find the predicted value using our regression line. So it's the actual, if you're a visual person, the vertical distance up and down from the actual point to the regression line that we put on our graph. And the residual is actually super helpful to determine if a linear model is appropriate for our data. So our formula is residual equals, and I already wrote it down once. I want you to remember the order is important. Actual minus predicted, or RAP. Actual minus predicted. So notice, remember I mentioned about that y prime. Y prime is the model, our regression line based on our sample data, but it's not what actually happened. It might not hit any one of our points, but it might fall right through the middle of that cluster of points. So if we're just looking at this, drawing residuals, notice I've got my scatter plot over here with just x values and no y values, nothing really in particular. I've got my regression line drawn in, so this is my y prime line, but this is an actual y point. So a residual is the distance vertically from my actual to my predicted. So this guy is right on the line. This guy has a tiny residual. This one has a larger. This one has a really large residual. It can be positive or it can be negative, but we definitely have distances from our actual to our predicted. So what is the name of the line drawn on the graph? We're going to call it a regression line, or maybe a least squares regression line, or a line of best fit. I'm going to stick with regression line or line of best fit. What does each dot on the graph represent? Important, keep in mind, it is one piece of sample data. The line represents our prediction of what that best fit is for that data. So letter C, it says to draw on each residual line. I actually did that already, so I skipped over that one. Which point has the smallest residual? It looks to me like this one right here has the smallest residual because it's closest or right on the line. Which point has the largest residual? I'm looking at maybe these two both have the largest residuals. We'd have to do the math and see the data to actually know. But they are farthest away from our regression line. So what does this mean? So I said the largest residual was something like maybe, I guessed it to be 6215 and 7252 probably. My smallest residual, it's like what, over 45 and 15 maybe for my ordered pair. What does this mean? It tells you the distance from the regression line. So if it's close to the regression line, if it has a small residual value, that means that it fits very nicely in that data. If it's far from my regression line, perhaps it's an outlier, perhaps it's skewing the data. Remember, we did talk about outliers and regression lines and correlation coefficients. So what we're going to have you doing, what I'm going to have you doing, is actually calculating the residuals, which means we've got to do some calculations for our least squares regression line. So to determine, first of all, if our linear regression, if our line, our regression line or our line of best fit is an accurate representation of the model, analyze the residuals by finding the regression line or our line of best fit, the actual equation, the y prime equals a plus bx. So that requires a little bit of work. We're going to use our formula, residual equals actual minus predicted, to find our residual values. How far is the actual from the prediction based on our line? We're going to plot our residuals on another graph. So we make a scatter plot, and then we make a residual plot. And then we're going to analyze the pattern of those residuals. So over here, these are residual plots, 4 of them. Notice I even have in this upper corner up here, they are all labeled with y minus y prime, right, which is the residual plot. So when we analyze the pattern of the residual plot, we are looking for what it looks like. So nice and neat and scattered means X and Y has a linear relationship and a line is the best model. Or the way I say it a lot of times, like in an assignment, I would say a linear model is appropriate. So when I look at these 4 examples, appropriate. When I look at these 4 examples that I've got up here, this one is the best scattered that I can find. So I would say that this would be a linear if I looked back at my original scatter plot. Notice for all of these too, this is 0. It's kind of like a 0 line. Usually you see it that way, because our residuals can be positive or negative, right? So notice on that scattered or that linear model, same number of dots above and beyond, there's no pattern. If you look at this guy, the second one, well, let me go down here. If there's some sort of pattern, that means a linear model is not best. And the kind of patterns I'm talking about are things like a Christmas tree, sideways, or a smiley face or a frowny face. Perhaps you're more technical and you see it as more of a parabola, but I like smiley face and frowny face. That means a linear model is not best. It does not work. So when I look at this, when I talk about a Christmas tree, this is what I'm talking about. Kind of flares out. There is a pattern to it, a triangular pattern maybe. This guy right here looks to me like I've got a frowny face or a parabola with a negative A, whatever you see. And B, I don't like B, I would say not linear, because I don't like that the dots aren't scattered evenly distributed between positives and negatives. It kind of has an upward trajectory. It almost looks like its own linear scatter plot. So I would not like this one, any of these 3. I wouldn't think that a linear model would be good for that. So we might have found a high R, we might have found our Y prime, and then when we go to do our residual plots, we're like, oh gosh, something just doesn't look right here. So then we look at that pattern. Scattered is good, evenly distributed between the positives and negatives, a linear model is appropriate. If there's some sort of pattern to it, we don't like it. Linear model wouldn't be best. We'd have to go to the next phase. All right, so absences and final grades, right back to it. So our residuals are calculated and shown in the table for example 10.7 along with the original scatter plot. So draw on the regression line. So we found our regression line, right? Our y prime equation, like 103 point something. So it was something like this maybe, probably a little better than that. Let me try one more time. And then this plot over here is our residual plot. So this is taking every one of our data points and showing the distance from our actual to our predicted. So I've got this point down here has a pretty big residual, somewhere around -9. I've got these guys up here, and then I've got those over there on the side. When I look at that, I actually don't really love my linear model for this because I see somewhat of a pattern. To me, that looks almost like I've got a low point, and then I've got a bunch in the middle up high, and then I come back down below my 0 line. So that almost looks like a frowny face. So I am not sure if a linear model is actually going to be a good representation. It's not appropriate. So we spent all this time. If I had a few more dots, say I'm going to take this guy off of here. If I had a few more dots evening it out like that, I might be happy. It's pretty scattered, dots above and below, no real pattern, but otherwise I definitely see kind of a parabolic shape to that. So I am not sure that linear model is our best option for this data. It looks pretty good, but maybe it's got some kind of curve. Maybe it's logarithmic, exponential decay, something like that. All right, so now let's get down to plotting our residuals. So we've got some information. So I gave you the data. This is my scatter plot, data A and data B. There's a lot of plots on this page, so let's make sure we've got everything. So I just typed in, oh, and I didn't fix these points. Isn't this a 3 and a 3.5? 3, 3.5. And I think everything else is good. I messed that one up, but I think I fixed it. So let's say I went through all the math. I did all the calculations. I did this scatter plot. I thought it looked pretty decent. Not a lot of pieces of data, only 5. But I did calculate back earlier when I had to that my R is 0.819. I did a test. I made sure that it was there was a significant correlation or a relationship between the two data A and data B. And so I calculated my y prime equation as 0.7 plus 0.7x. So my y-intercept is 0.7 and my slope is 0.7. So my line would go something like, let's see, like this, if I were to draw that in. So with that being said, I've got a pretty good idea. So I know that I've got some residuals. So it says to complete the table with each residual value. So here's the thing. I'm going to type in, this is my actual. I'm going to calculate my predicted, and then I'm going to subtract. Actual minus predicted will give us residual. So I had to know this regression line in order to do this problem. So all of my x's are, I tried to make them easy, 1, 2, 3, 4, 5. I'm going to go ahead and I'm going to actually use this equation. So I'm going to put a 1 in for the x. So y equals 0.7 plus 0.7 times 1. I'm going to do that calculation. And my predicted y prime is a 1.4. My predicted, when I put a 2 in for the x, was a 2.1, a 2.8, 3.5, and a 4.2. I forgot to write in my actual y values. This is from my data. This is from my ordered pairs that I gave you that we started off with. So my actual data, this was the data that was given, was what, a 2, a 1, a 3.5, 3, and 4.4. So now I'm going to go ahead and I'm going to do residual equals actual minus predicted. So 2 minus 1.4, 1 minus 2.1 does give me a negative. Keep that in mind. 0.7, a negative 0.5, and a 0.3. This is what goes on my residual plot. So I have to keep my x values because that's my independent variable. And then I use my residual values as my y-axis for my residual plot. So if I scooch up at 1, let's see, oh, I guess I didn't label this very well, right? We'll make this 1, 2, 3, 4, 5. And then I've got a 0 in the middle. We'll make that 1 and 2, -1 and -2. So with my 1, for my x value, my residual value is 0.6. So over 1 up 0.6. For 2, my residual value is a -1.1. For 3, my residual value is 0.7. 4, I've got a -0.5. And 5, I've got a 0.3. All right, so here is my residual plot. So now analyzing the plot is just asking, is a linear model appropriate? Is it scattered or is there a pattern? So I think that it looks pretty good. I know with only 5 points on there, it's not super great, but I think that a linear model looks pretty good. There's a scattered pattern. So a linear model is appropriate. I can only find a residual if it's an actual piece of data, right? I can't do something that I don't have an actual piece of data. So I have to only stick to the data that's given to me that I've collected. And then obviously, if I'm going to find my predicted value using that y equals 0.7 plus 0.7x, I'm just going back to the last section, a little extrapolation again. I could find the predicted value. So I could say y prime equals 0.7 plus 0.7 times 20, calculate that out, and my predicted value would be 14.7. I don't have an actual value for that, so I can't really go anywhere else with it. So that's what we're going to look at for residuals. We're going to calculate residuals, make residual plots, and decide if a linear model is appropriate. And that is it for section 10.3.